Welcome to Math 106, Chapter 3.2, where we talk all about the chain rule. Now, we've seen the chain rule ever so slightly in some previous videos, especially the one right before this. We also saw a little bit of it in chapter, I want to say it was like 1.6 or so, where we couldn't derive your variable straight away. We had to apply other rules. More likely, it was the power rule before we got to derive. Now, before we launch into that explanation, let's have you try a warm up with example 1. You'll notice that we have these composite functions right here. So it says find f of g of x. So go ahead and pause video, try out your composite function. So if we're taking your g of x, which g of x is going to be this whole thing, x squared plus 3, we're going to work it inside each and every x value that we see in f. So x minus 1, the x is now being replaced with x squared plus 3, your g. Minus 1 up top. We're going to do the same thing down below. X squared plus 3, and then plus your 1. So these are just getting replaced by your g of x. Now we can go ahead and simplify. X squared plus 3 minus 1. X squared plus 3 plus 1. So we get x squared plus 2 over x squared plus 4. Now this is a composite function of f of g of x. So we have now composed these two functions. Now what's going to happen is that in our next chapter is that we already have this composite function, and we are going to try and break it up into its parts. So looking at the chain rule, right, thinking about a composite function, we need to use differentiation techniques. So let's write the following functions as composite functions similar to the one above. Hint, use order of operations. So let's see if we can pull apart your function here. Could you make two functions given that we have one function here? Well, one such function would be this inside portion. We can call this inside portion g of x. And let's say we took away all of g of x, what would be left over? We would have parentheses and then raised to the 8. This empty gap is symbolizing, or can be thought of as, just the step right before, right? Opening up this parentheses, leaving a gap, and then making, putting our value in. So our leftover bit could be thought of as x to the 8. The reason why there's an x there is that because if the leftover bit is parentheses to the 8, right, we need to symbolize that there is a function on the inside. So right here, x to the 8. Let's see if you can try it again with b. So let's pull out your inside function for x plus 1. And getting rid of your inside function, what is left over? Well, that would be this square root. And again, that gap is symbolizing another variable. Now, keep in mind, with your composite function, what we have formatted is f of g of x. And again here, f of g of x. Because, right, the inside function, g of x, right, that is in fact your inside function, right? You've pulled it out from the inside, meaning that whatever value that we have for x, it needs to go through g first, and then we can go ahead and take it to the 8th power. Or simplify g first and then take the square root of it. G is always affected first. So for example, if I were to evaluate f of g of 3, actually, that's not a good one. Let's say f of g of 0, we'll do 0. We need to first evaluate g of 0. 4 times 0 plus 1, which is just 1. So now we can evaluate f of 1. So now the square root of 1. And if we did it all together at one time, the square root of 4 times 0 plus 1. Notice that your g, again, is being affected first, right? Order of operations. Now that you have your simplified form, then we can go ahead and take the square root of it, the square root of it being f of x. Now, how that relates is that the chain rule, we differentiate first the outside function. So before you get to touch these inside functions, you first need to derive the outside. These have your exponents, right? Your power rule. So first derive the outside function f of x. Substitute g of x for all x in the result. Then multiply the derivative by the inside function symbolically. So if you have some sort of a composite function, we can think about it as taking the derivative of the outside, leaving the inside underived, and then multiplying it by the derivative of your inside. So in effect, we're using the power rule, more likely. Keeping the inside the same, then derive the outside. So let's go ahead and see that in action. So in example 3, use the chain rule to compute the derivative of f of g of x, where f of x is x to the 8 and g of x is equal to x to the 5th plus 9x plus 3. So they've already told us, in most cases, we're not going to tell you what f of x and g of x are, but we've already picked it apart from our previous example here, right? We've already picked it apart. So we can see that there are 2 functions here. So can you go ahead and derive x to the 8th power? Well, that would just be 8x to the 7th. Now, if we know g of x is x to the 5th plus 9x plus 3, can you go ahead and derive g of x? Well, g of x would be 5x to the 4th plus 9. And keep in mind your chain rule. If your chain rule, we said to derive the outside function, keep the inside the same, then derive your inside function, right? It's kind of a cause and effect. I think we use the treasure chest analogy, right? Which I'll kind of walk you through what we have without the chain rule. But it just says, okay, take the derivative of f of x. So that would be right here. That would be 8, leave a gap, x to the 7th. But keep in mind, on the inside, there is g of x. So we're going to replace that x with your g of x, keeping it underived. And that's coming from here. Lastly, we can take the derivative of g of x. And that would be your chain rule. Now, because there's nothing else to simplify here, we want to keep it in its factored form. By no means do we want to distribute this 8 into this function and then multiply this out 7 times. That would be extraordinary. Now, to see it in action, so if we had h of x, which we know from previous example was such, to see it in action without having to break it up, which this is my hope that by the end of this lecture, you can do it in this such way, is that keep in mind that treasure chest analogy. In order to derive, you have this power rule in that's kind of in the way. So you need to break the lock on your treasure chest. You haven't touched the treasure quite yet. The treasure is us being able to derive. Now that you have derived with the power rule, right? Our lock is now open. We can lift the lid and now go ahead and get the treasure. We can go ahead and derive. So deriving your inside, we have 5x to the fourth plus 9. You'll notice that those examples or those equations or answers should in fact be the exact same. One is just breaking it up into functions. The other is just to apply the chain rule kind of as a cause and effect. Let's get some more practice. So it says dy du. So find dy du if y is equal to such and u is equal to such. Now, there are a couple methods in order to implement this. Now, if you're, excuse me, there are a few different methods to implement this. If we're looking for dy du, and they already tell us what u is in effect, your first method could be to to substitute I'll just keep it one more time. To substitute u of x squared plus 1 into y. And then derive all at once. So let's see that in effect. So if we have y is equal to, instead of u to the fifth, right, and u to the third, we're going to instead take what u is actually equal to, x squared plus 1, and then raise it to the fifth power. So you can see that we've now inserted your u. We're creating a composite function. We haven't derived quite yet. Do the same thing to the other u, x squared plus 1 to the third. One more, there we go, plus 8. Now that it's in there, we can go ahead and derive y. Now, using the chain rule to derive y, right, we can think of, okay, that treasure chest, breaking open your lock. Now that the power rule has been completed, right, you've now broken open your lock, you're lifting up the lid, we can go ahead and derive the inside. Do the same thing on your next one. Minus 2, the 3 comes down. Open the lid, derive, and the 8 is a constant. So now let's go ahead and clean up. Let's see, that would make 6 and then 2, so that's going to be 12. Now let's go ahead and clean up one more time and start to simplify. So pause the video, see if we can simplify here. So we have 10 and 12, so we can take out a 2 from each. We can also take out an x from each. We can also take out an x squared plus 1. This one has 4, this one has 2, meaning that we're going to take out 2 of them. So leave 2 behind in its place. So if we've highlighted what we took out a 2, an x, and then we're leaving behind 2. And again, 2x and that whole thing. So we left with a 5 and x squared plus 1 squared minus a 6. Now we can keep it like that. If you want to, however, you can FOIL and simplify a little bit further, but this is probably as far as I would suggest you go. Now this is just the first method if we're told that u is some sort of separate equation, and then we're looking to derive u in terms of y. So one thing we can do is to substitute u in and then complete the derivative. The alternative method is to derive separately and then multiply the derivatives and substitute. So what that's going to look like is we know that y is equal to u to the fifth minus 2u to the third plus 8. So derive it separately. Go ahead and derive. We have 5u to the fourth minus 6u squared plus 0. And that should kind of look familiar with the 5, the 4, the 6, the 2, which is being completed right here. Now let's go ahead and do the same thing with u. We know u is x squared plus 1. So go ahead and take the derivative of u. Derivative of u is just 2x. Now, in order to get dy du, if u is in different terms, right? dy du can be multiplied by du dx. The reason for that is that u has a different variable. It's a different function. And keep in mind, if we're multiplying these two together, notice that in terms of simplifying, that we'll end up with dy over dx, which is exactly what we have over here. If you didn't notice, right, we substituted with u, but now all of a sudden we're working with a variable x. This is how we end up getting dy dx. Because here we have du over dx. We derived your x in terms of u. Over here, we have dy over du. So we derived y, but in terms of u. Now let's go ahead and multiply these two together. 5u to the fourth minus 6u squared times 2x. Now we know that u, maybe put it in orange. Nope, one more time, orange. We know that u is actually equal to x squared plus 1. So we can go ahead and substitute that in, x squared plus 1. And last thing to do is to look inside your parentheses and see if there's anything that you can pull out. Is there anything that has a similarity? Well, that would be this x squared plus 1. There's 4 here and there's 2 here, meaning that we're going to take out an x squared plus 1. We're going to take out 2 of them, leaving behind 2 here and none here. You'll notice that those two are the exact same. What I recommend is probably method 1, substitute it in and then derive all at once, especially if this was kind of too much for you, especially this portion, when we derived it in terms of dy over dx. Now, in many situations involving composite functions, the basic variables in is time t. It may happen that x is a function of t such that x is equal to g of t. So x has some sort of a time value. Some other variable, let's say this one is r, is a function of x that is r is equal to f of x. So r contains the variable And x has some time connotation. Hopefully that's how you spell connotation. Therefore, if we have r, and r is equal to typically f of x, right? But keep in mind, x is equal to g of t. So r is equal to f of g of t. So the chain rule says that if we have r of t, we need to first derive dr dx and then dx dt and multiply those together. That way these can cancel and create dr over dt. So all this is saying, kind of full circle, is to compose so that all have one variable. I'll have one variable. Now I may have noticed my mistake from earlier, and it's in the notes when it says find dy du. This should actually be dy dx, because otherwise dy du you would derive this one, but it should be dy dx, and I must have forgotten to change that last semester.